Hi guys, welcome to this presentation on feature engineering, essentially the filter methods under feature selection. As you know, feature feature engineering is one of the key aspects of machine learning and almost all of the AI applications. So in this presentation, we'll continue our discussion on filter methods. Essentially, in the previous two lectures, we covered variances and what's the use of assessing variance in terms of machine learning and also assessing covariances. In this lecture, we'll talk about correlations, which is simply a normalized value of covariances. But along with correlation, we will also talk about a side topic called multicollinearity, and I'll show you the Python code to demonstrate these side effects or the dangers of multicollinearity. Okay, so in our previous lecture, we talked about covariance, which is essentially a metric or a scalar value talking about the direction of relation. If one variable is changing, the other one is also changing in the same direction or in the opposite direction. But covariance doesn't talk about the strength of relation. Correlation is the metric that we use to check not only the direction of relation but also the strength of relation. So let's take a look at what is correlation, which is essentially a covariance, but this time it will give you a measure of strength and as well as directions of change. So it's essentially a normalized value um, of covariance, and the range of value for correlation would be -1 to +1, and we'll discuss why it is -1 and +1. Close to 1 is a strong positive. Similarly, close to -1 is also strong, but in the opposite direction, which is a negative direction. Close to 0 is a weak or no correlation. In fact, close to zero point 0.4 plus and minus indicates a very weak correlation. So correlation, let's take a few examples here. Let's say the calories you intake, and that has direct correlation with the weight. Similarly, the eye color and your relative's eye color probably also would be similar. So that exhibits correlation. Amount of time we study and the marks that we get or grade that we get also has correlation. So let's see how we compute correlation. Essentially, it's a normalized version. So covariance, you use covariance and then divide the covariance by standard deviation of those two variables. So for example, here, so the numerator is going to be your covariance of two variables, and you divide it by the denominator, which is basically standard deviation of column 1 and standard deviation of column 2, and that gives you a standardized or normalized value. Since the direction can be positive and negative, hence the range is going to be from -1 to +1, and correlation does not have any units because you are dividing it by the standard deviation. So the formula is quite straightforward. Let's say you have two columns. Take the mean of column 1, mean of column 2, and find out the deviation of each of the column. Multiply the deviations, and that's going to give you covariance. Add all of these covariance, and this is your total covariance. Divide by the number of samples, will return you the covariance, and then further divide by the standard deviation of column 1 and column 2 will result in a value between -1 and +1, and that's called correlation. So finally, this is what the representation is. So the numerator is nothing but your covariance. Denominator is divided by the standard deviation of column 1 and standard deviation of column 2, and that returns you a correlation which is between -1 and +1. The values closer to -1 or values closer to +1 is considered a strong metric, whereas values in between, like 0, is a weak or no correlation. Just a sample example here, like perfect positive correlation would be very close to 1. Highly positive would be somewhat like this, but still very, very clear direction. Low positive also has direction, but kind of spread out. No correlation here. That was low. And this is no correlation here means perfectly random scatter of the point in the column 1 and column 2. Negative, slightly low, would be a little bit scatter, but still gives you some direction. And high negative has a more prominent direction, and the perfectly negative correlation is exactly a straight line, which probably never happens in the real world, but just to illustrate the point. Something very close to covariance or correlation is a topic of multicollinearity. And we will see the difference between the two here. The covariance is between the two variables. The measure or the strength or direction is going to give you the metric for covariance and correlation. And covariance typically takes any number, but correlation would be between -1 and +1. And you have positive and negative and 0 covariance. Compared to this, the multicollinearity is almost similar. It's a degree of correlation, but between two or more independent columns. That means when you have more than two columns, like 3, 4, 5, and those 3, 4, 5 columns within themselves impact each other in terms of relation or correlation, that phenomena is called multicollinearity. This is a big concern in machine learning models. So it's very important to understand multicollinearity and then detect the strength of or the level of multicollinearity, apply domain knowledge and a data knowledge, and then take the corrective actions. So there are multiple ways we can detect the multicollinearity in the Python code demo, which I'm going to do right now. Just after this, I'll show you those couple of methods that we use to detect the multicollinearity. As an example, the multicollinearity can be depicted. Let's say you have these columns as independent columns or predictor column, and the Y is a response column. Now, if you have correlation within these x's like x1, x2, x3, and x4, that's multicollinearity. So essentially, we want a relation between the predictors and the response variable to be strong. And the relation within the predictors is called multicollinearity or redundancy. And this is the real problem in most of the AI or machine learning or deep learning applications. So it's a huge practical problem. And essentially, the presence of multicollinearity means is going to inflate the coefficients of the predictor variable. So your predictions will not be stable. And there are few ways that we can use to handle multicollinearity. Some of these are called regularization techniques like ridge lasso. Those are topics that we will cover shortly in our video series, essentially the embedded method. Choice of machine learning models also is one very good option, let's say extreme gradient boosting or some of the ensemble methods to handle multicollinearity. So next, I'm going to use a Python, and a little bit of NumPy and linear algebra to demonstrate what is multicollinearity, how do we detect multicollinearity, and what's the impact of multicollinearity. Okay, so let's take a look at this sample demonstration using NumPy essentially, and also some SciPy as well. So both of these can be used. Either you can use linear algebra package, or you can use SciPy as well to do the same. Now in this demo, I'm going to show you a few methods to check multicollinearity. One method is called eigen decomposition method. The second method is called VIF method, and the third method is called condition number. All of these are very um, heavy statistical topics. So request all of you to look into these specific areas like eigen decomposition and the variance inflation factor and condition number. I'm going to use all these three methods to detect. Now some random data. So I've generated some random data. Sample is 10. There are 4 columns. So this is how the data is looking like. And again, some random numeric value as the target value. The first step is to compute the correlation coefficient of the data. So you pass X, and this is your correlation coefficient. Since there are 4 columns, so you get a matrix of 4 by 4. Most of the feature engineering tasks are based on correlation. For example, principal component analysis, linear discriminant analysis, and some other factorization method. They use the same construct. The first step is to check the multicollinearity. Here, the method is eigen decomposition. And in order to do eigen decomposition, I'm using a linear algebra package here and an eigen function. Pass the correlation matrix. And that's going to return you the eigenvalues and eigenvector. So in this data set, firstly, um, originally, these are all random numbers, so they will not be exhibiting any multicollinearity. And you can see here, so when I run this function, I get discrete value in the eigenvalue vector. That means none of these are close to 0. That means no presence of multicollinearity. And for each of the eigenvalue, these are eigenvectors. For example, this one, and this is eigenvalue, and this is the corresponding eigenvector. These two we are going to use in this example here. So there is no multicollinearity originally, and similarly we can use the VIF method, and again a function here, and pass the data, and it's going to return you the VIF of each of the column. Now you notice here the VIF of greater than 5 for each of the column will indicate presence of multicollinearity. Notice here none of these values are greater than 5, so that means there is no multicollinearity. Again, the condition number is another method to check the presence of multicollinearity, and this one requires a value greater than 30 to say that there is multicollinearity. Here the value is 4.4, so pretty okay. Now what we're going to do is we'll apply linear regression on this data set and compute the beta coefficient. So this is your beta coefficient for column 1, column 2, column 3, column 4, and this is a manual method to compute the beta coefficient. And you can check by using the scikit-learn package, linear regression. You pretty much get exactly the same value here. Okay, so that means these two methods. In fact, scikit-learn uses this formula inside the algorithm to compute the beta coefficient. So on our original data, this is our coefficient. Let's introduce some collinearity. In scenario 1, we will have 2 columns collinear. We'll create one column which is similar to an existing one. So for example, I'm going to create column C4, which is going to be similar to C1, and we add a little bit of noise to make it somewhat different. So that's your new data set, X new. And now we're going to check the eigen decomposition. And you look at carefully, here I'm getting a value of 0. That means there is a presence of multicollinearity. Look for the vector and specifically look for the values which are non-zero. And those are the columns that we actually used in our formulation here. So if you notice here, the column C4 is equal to C1. So this is C4 and this is your C1. This is pretty much the same thing that you defined in the equation, and this package is detecting the presence of multicollinearity. Let's look at the VIF method again. So VIF method is for column 1 and column 4 is showing very high value. That means there is multicollinearity. So what's the impact of so? Even the condition number is very high. So that means there is presence of multicollinearity. All right, now what's the impact of this? So when you run your regression model on such data which has multicollinearity, look at this output here and pretty much the same output from linear regression. But with multicollinearity, if you look at it, we got the coefficient of this, and now you match here, the coefficients are nowhere similar. In fact, the coefficients have really gone up in many cases, and sometimes for some column, the directions have changed. That means multicollinearity is quite a danger in machine learning. So let's do a slightly difficult proposition with scenario 2. Now we will have column 1 which is similar to couple of columns. So let's say C4 is similar to C0 and C3 and little bit of noise. Now you notice here I'm going to get the 0 here because of multicollinearity, and again if you look at it carefully, this eigenvalue and this corresponding eigenvector, this is non-zero, this is non-zero, and this is non-zero. So this one is C4 and this one is C3 and this one is C0. That's what you have it here. So we defined C4 as the equation of C0 and C3, and that is what is being detected here. Now, what happens, even the condition number and VIF show the same. Now look at the coefficients. They are again quite different than the original one. So level of multicollinearity or depth, or you can say strength, or you can say degree, or whatever you call it, the amount of multicollinearity really impacts the machine learning model in terms of the coefficient. And if you have picked up columns which are really not required for your machine learning model, and if these columns become or they are multicollinear, then these coefficients cannot be trusted. Now let's go a little forward with this scenario 3. This time we will define a perfect multicollinearity. Now this can be very, very dangerous. So with this, again, the check for eigen, value. Again, you get a value of 0. And VIF also shows. Now VIF is resulting in some error because of perfect multicollinearity. Now look at the condition number, pretty high. That means there is a very severe multicollinearity. But the problem happens here at this stage when you really compute the coefficient is going to result in singular matrix. The reason it is happening is one column can be perfectly defined as an equation involving other column. If that is so, the matrix decomposition is not possible and you're not going to get a perfect solution for this. Now, in order to address the multicollinearity, there are many methods. One of the method is to really study what are the redundant columns. Can we remove some of these unnecessary columns or not? Or sometimes you can do some transformation, combine these columns to make one column. Some of more methods is collecting more data, probably can reduce the effect of multicollinearity. Plus, you have other methods like regularization, which we will talk about in the subsequent lecture. Choice of machine learning models is also one of the options to handle multicollinearity. I hope this demo was useful. So the key takeaway is when we analyze our data and choice of machine learning, multicollinearity is one of the significant exercises that we have to carry out. Okay, so that was a quick demo on multicollinearity and the impact of multicollinearity on machine learning models. I hope you enjoyed this session. Next, we will talk about the type of correlations in the next lecture. See you then.